related and equivalent statements. Now, related statements, we learn about implications if P then Q. Now, its converse is just the reverse of the statement position. So we say if Q then P. Inverse is the implication but with negation. So if not P then not Q. And contrapositive is the negation of converse, which is not Q then not P. All right, so let's look at this same sentence again. Consider the same sentence. If I win tickets to Coachella, then I'll take my friends. So learn how to write converse, inverse, and contrapositive statements. To write converse, the converse will sound like this. If I take my friend, then I win tickets to Coachella. Inverse will say, if I do not win tickets to Coachella, then I will not take my friends. And contrapositive will say, if I do not take my friend, then I do not win tickets to Coachella. Okay, so now when we're looking at if suppose P and Q are statements, create truth table for the converse, inverse, and contrapositive, right? Which statement have the true same value? Now, if you look, okay, so the first one is the implication. This is what the converse. This is the this is a converse, this is the inverse, and that's a contrapositive. Now, which one are the same value? When we say same value, how do you know something's equivalent? Equivalent statement means they have the same resulting column. Okay, so if you look at implication, it's true, false, true, true. So the only one that look exactly like this one is actually the contrapositive, true, false, true, true. So the implication for this statement and its contrapositive are equivalent. Okay, so that's what equivalent is. Now, argument. Okay, so when we talking about argument, the logical argument is something that if you are giving statement, a number of statements, and want to know if the logic flow is correct. So, for example, okay, well, a couple of things we need to learn first. There's inductive and deductive reasoning. Now, inductive reasoning is using something that you have examples. Okay, you look at many examples and then you come up with a conclusion. For example, like this first example here, the premises is if I forgot my purse last week and I forgot my purse today, the conclusion is I always forget my purse, right? Because there's examples of this the example from previous actual example to kind of leading to your conclusion, right? You always lose your purse. Now, versus something more like, okay, deductive reasoning, where you're using statements, not specific examples. For example, all cats are mammals, or a tiger is a cat, therefore a tiger is a mammal. Okay, so that we didn't use, we use a statement, logical statement to reason it out, to say this argument here is valid. Okay, now to find out if argument is valid or invalid, we can reason it out, or sometimes we can use our Euler circle, right? Now the Euler circle is very similar to the Venn diagram you used before. So if you look at this this argument here, someone argued that no cows are purple, Fido is not a cow, therefore Fido is purple. Now, is that true? Is this a sound logic? Well, let's take a look at this argument. So no cows are purple. So we have a cow and we have purple. Now, since no cows are purple, purple and cows would not have any intersect, right? They will not overlap because none of the cows are purple. Now, Fido is not a cow. All right, so we know Fido is not a cow. But the way you draw this Fido circle here, you can either, sometimes you can draw it out here. As long as Fido is not inside or crossing into cow at all, Fido is not a cow. But Fido's cow could be out here. That means, well, Fido doesn't have to be purple. So it depends on what happens. If you look at the circle here, if you draw a circle here, if Fido is here, then it's not purple. If Fido is on this side of the circle, then Fido would be purple. So the fact that we say Fido is purple is not always true. Therefore, if something is not always true, it has to be always true. If it's not always true, then the argument is invalid. Now, we can always use truth table as well. Alright, so here's another argument. If someone argues that if I have a shovel, I can dig a hole. I dug a hole, therefore I had a shovel. Well, you just think about it for a minute. That's not true, right? Just because you dug a hole doesn't mean you have a shovel. But let's look at what truth table says, okay? Just follow the logic. Now, the way we do this is if then, right? So if I have a shovel, so that's our conditional statement. So P is you have a shovel, and Q is digging a hole. All right, and I dug a hole, that's why it's Q. Now, conclusion, we will draw a line for conclusion when we do arguments, okay? And then therefore I have a shovel, which is like you're having a shovel is P. Okay, so the way you rewrite this, so what we did, step one is taking your argument, changing to our logic notations, P and Q. Then how do you put all this into a logical statement? Then instead of writing it this way, we can write if P then Q and, okay, this is and, okay? So when we do argument, these two is always and. So and Q, so if P then Q and Q happens, therefore, now we see this double bar with the arrow. This is the same as just single bar. Okay, we just use double bar in arguments. So this is really if and then. Okay, this is a conditional statement P. So if you want to read the whole thing out, it will be something like this: if parentheses if P then Q and Q, therefore or then P happens. All right, now our job will be, well, let's take a look at this and see if this statement actually sound, this argument, right? So we've done this before. P and Q is true. That's how you set it up. Now let's do what's in the parentheses first. If P then Q, the only time P then Q is false is true, false, false. All right, we're done with that. What's in the parentheses? Now we're going to do a conjunction and Q. Now and Q, these two and has when for and to be true, they both have to be true. So only time that happens is the first column, I'm sorry, the first row and the third row. They're both true. So now we have true, false, true, false. Then we take this whole statement to the left and we want to make it if then P. Well, if then again is what? True, false, false. So if you take a look at this statement and the original statement P here, make sure this is the first statement, that's second statement. So you're looking for true, false. So this is true, true, that's not okay. This is only one right here, true, false, false. Now, because this is false, if you look at the entire conclusion, this is not a tautology. Now, tautology means everything has to be true. If everything is true, or if it's a tautology, then we say this argument is valid. But because there's even, just take one, even if there's one F, all right, then the whole thing is now invalid. Now the syllogism, right? We've done this. This is a famous syllogism. If P then Q, here's another argument. Okay, we call this argument syllogism. If P then Q, if Q then R, therefore P then R. We've done this in geometry. We've done this in transitive property. For example, if A equal to B, B equal to C, therefore A equal to C. You heard that before. Okay, same thing here. If I go to a party, I'll be really tired tomorrow. If I'm really tired tomorrow, I saw my friends. So conclusion is, if I did not see my friends, I did not go to the party. Okay, so this is one way of using syllogism. Okay, and syllogism is always valid. Okay, we just want to show you a couple of the commonly used argument that's valid. Okay, and on the other hand, these are commonly used logic that's false. Logical fallacies in common language. All right, so you have a lot of these. Okay, I strongly suggest you take a look at all the definitions. Okay, which one is which one, and I have some example for you how each one. This is a definition, and these are the example for how each one is used.